Are they in row reduced echelon form or not? Okay, so anyone have an opinion on the first one? Is it row reduced? Yeah? Yep, so I agree with the thumbs up. This is row reduced echelon form. And, you know, suppose this came from a system of equations with 3 variables, x, y, and z. So what would be the solution to this? So x equals something, y equals something, z equals something. Yeah. Exactly, yeah. Right, because one way you can kind of think of this is this equation says, because this is like the x column, this is the y column, and that's the z column. So what this really says is 1 times x equals 0. This equation says 1 times y equals 3. This equation says 1 times z equals -2. Okay, so indeed, yeah, that's the solution. Is this one in row reduced echelon form? Let's maybe from the audience, thumbs up or thumbs down. A lot of thumbs down. I've seen some thumbs up. I guess what you should think about when you want to know if this is in row reduced echelon form or not, you should think, is there anything I could do to this to simplify it at this point? And if you think about it, there kind of isn't. Because, I don't know, like, if I look at my first column's fine. It's, the first row has a leading 1, and then all of this is all 0. My second column, so the second row has a leading 1. In the second column, everything else is 0. And I've got a row of zeros at the bottom. So like, normally in this Gauss-Jordan elimination, what you would try to do, if you got to this matrix, at this point you'd look at this column and try to get a 1 here. But you kind of can't do that without messing up the other stuff you've already done. So actually this is row reduced echelon form. Okay, so there's 4 criteria for that, right? So the criteria are all the rows of zeros are at the bottom. That's satisfied. The rows of zeros are at the bottom, right? The second criteria is every non-zero row has a leading 1. Well, there's a leading 1 here. There's a leading 1 here. That's satisfied. This third condition is that the leading 1s, as you go down the matrix, the leading 1s move to the right. So, and that's true, right? I've got a leading 1 on this here, and then the next one is to the right. And if we had more, they'd have to go kind of to the right, to the right, to the right. And the last condition is whenever you've got a leading 1, everything else in that column is supposed to be 0. And that's true in these 2 columns. So this is row reduced echelon form. The solution to this one is not quite as simple as before. So here we had so one thing about this previous example is that the solution was unique, right? There's only one choice of x, y, and z that satisfies this. In this case, we're going to have infinitely many solutions. Okay? So generally, when you have a unique solution, you're going to have a nice thing like this where every column has a 1, and these equations tell you what the variables are. In this case, this is basically, when you have infinitely many solutions, it's going to look like this. You're going to have, you know, only 2 of your columns have a 1. So this is the column for x. This is the column for y. This is the column for Z. Only two of them have a leading 1, and the last one doesn't have a leading 1, and then you've got maybe some zeros at the bottom and stuff like that. So to figure out the solution, what we can do is kind of write down what do these equations say. So the first one says that x plus 3z equals 2. Okay. What does the next equation say? Yeah. Exactly, yeah. Now the third row says something really peculiar. All it says is 0 x plus 0 y plus 0 z, so 0 equals 0. So this says nothing, basically, right? Okay. So what this actually kind of, and basically what this does, it doesn't tell us what z is, basically, right? In this other situation, this tells us what x is, what y is, and what z is. This one sort of doesn't tell you what z is. But what that actually means is that z can be anything. Okay, so the solution is going to be, so my solution is going to be that z is equal to, let's just call it t, for any real number t. Okay. And if z is equal to t, then what x will be, if I solve this for x will be 2 minus 3t. If I plug in t for z and I solve that equation. And y is going to be 3 plus 4t. So these are you've now got infinitely many solutions. Okay. So this would be, okay, so the answer to this true or false, like is it row reduced echelon form or not, would be yes. And then if you were asked to find the solutions, this would be your answer, that x is this, y is that, and z is that for any real number t. Okay. So that's basically what's going to happen if you get into one of these situations where your equation, there's one of the variables in your equations, they don't say anything about z. Like they don't, I mean, in some sense it does say something about z. But basically if you end up with just like, you know, it doesn't pin down exactly the value of z, then it could be anything. Yeah. Yeah, that's a good question. In some sense, there's not really a great reason for that. I guess it's just sort of clarifying that like z is the variable that was in our original equation, and now we're just saying z can be anything. I don't know. Yeah, you know, I guess it's just clarifying that z could be any real number, but yeah, so you should just kind of remember to write it in this form, but you could have just said, in some sense, you could have just said z is any real number, and then, but it would kind of mean the same thing. Yeah. That's a good question. Actually, that's what's going to come up in this third example. Yeah. Yeah, and that's a different story when that happens. But are there any more questions about this one in particular? Or, okay. So basically, when you do these examples, you want to row reduce until you get into row echelon form. If you see something like this, you know it's a unique solution. You see something like this, infinitely many solutions. So here's a question. Is this one in row reduced echelon form? Would you say? Thumbs up, thumbs down? Yeah. I think, yeah, most people would, I guess, agree this one's row reduced echelon form. You can't simplify it any more than this. This is already pretty simple, right? And this one has some similarities to the previous example, except now this issue that you're mentioning is coming up. That on the bottom, we've got something that says 0x plus 0y equals 4. Yeah? It's not, it's actually something weirder than that. I mean, basically, this third equation says, so actually in this first situation, we kind of had a constant, like we kind of had one solution or something. But what this says is that 0 equals 4. And we're pretty sure that's not true, right? So this is nonsense. What that means is that there is no solution. So if it asks you to find the solution, your answer should be there is no solution. So you shouldn't give any kind of specific answer for this one, right? I mean, like this is saying x is 2 and y is 7, but I wouldn't even, to be honest, I wouldn't even write x is 2 and y is 7, because really, when you see this row, you should say, none of this is valid anyway. There is no solution to this, if that makes sense. Yeah? Yeah. If you get a row of zeros on this side, and then here it's not a 0, there's no solution. What about this one? Oh yeah, by the way, the answer to the row reduced echelon form was yes. It is in row reduced echelon form. Row reduced echelon form, yes or no? Thumbs up, thumbs down. Yeah. So this one definitely is not in row reduced echelon form. Any specific reason or any problem you see with it? Yeah. Yeah, the problem is totally the second column, that I've got this nice 1 here, but I haven't gotten rid of this -2. So this is a column that contains a leading 1, but the rest is not 0. So so this is no, because essentially what you should think about when you're doing this is, if I had this matrix sitting in front of me, could I simplify it more? And the answer here is yes, because I could just take 2 times this row and add it to this row. It would simplify it a little bit more. You'd get a 0 there. So this is not in reduced row echelon form. And again, this is another example where there's no solution. Again, because 0 equals 2 is sitting right there. Yeah. In theory, you could probably logically figure out what the solution is, but usually on these questions, you're going to be asked, use the Gauss-Jordan elimination, which means get it to row echelon form, reduce row echelon form. So I guess technically you can probably find the solution, but you shouldn't do it that way. You should always go to reduce row echelon form and then figure out the solution from that, because that's what you're going to be expected to do. Any questions about any of these? Okay. One thing to notice, most of these had 3 variables, 3 equations, right? Except this one was a bit different. It had, so this one only has 2 variables, x and y, right? And 3 equations. Maybe it's worth saying, so, there's sort of slightly different possibilities that can happen depending on how many equations you have and how many variables. So let me just say, if you have if you have the same number of equations and variables, okay, there are three things that can happen. So you can have a unique solution, okay, and that's when it's going to look like, for example, 1, 1, 0, 0, and then some numbers here, for example. You can have no solution. So that, for example, could look like you've got some zeros on the bottom and then something non-zero here, and it doesn't really matter what's up here, right? Or you could have infinitely many solutions. And that's maybe where you've got, and then it doesn't really matter what happens elsewhere. Okay. So that's if you've got, let's say, 3 equations, 3 variables, or 2 equations, 2 variables, 4 equations, 4 variables, right? If you have more equations, than variables, actually the possibilities are kind of the same. So you have the same 3 possibilities. Okay. But one thing to maybe remember, if you have more variables than equations, you can only have no solution or infinitely many solutions. Okay. You can't have a unique solution. I guess if you think about it, I mean, if you think through an example, so imagine you have 3 variables and only 2 equations. You could have, for example, this, right? So this is now 3 variables, 2 equations, right? Or let's make it a bit more complicated here. I'll put a 4 here. Right? So what this would be saying, so like what this is saying is that you've got x is equal to 3 and y plus 4z equals -1. But again, it doesn't say anything about z in some sense. It doesn't say z has to be some number. Okay, so then you have infinitely many solutions. Your solutions are x is 3, y is -1 minus 4t, and z is t for any real number t. Okay. So infinitely many solutions. And if you think about it, if you've got more variables than you have equations, you can never, your equations can't determine all the values of all the variables. So yeah, you're always going to have infinitely many or no solution. Okay. I feel like I'm kind of saying that a bit fast, but any questions about that? Yeah. Yeah, with more equations than variables. Or sorry, so are you asking about which the possibilities you can have, or? Yeah, you would do things in sort of the same way. I mean, it's kind of so this is one example where you've got 3 equations and 2 variables, and basically at the end of the day, you could have, so this would be like no solutions. You could have a unique solution. For example, if I had all zeros here, then if this was all zeros, then now I don't have a contradiction anymore. This just says 0 equals 0, and that's fine, right? So then you'd have a unique solution. Which is just like x, 1 times x, right, equals 2. So x is 2. 1 times y equals 7. Y is 7. And there is no z because I've only got 2 columns here, right? So this would just be my solution. But you could also have infinitely many solutions if, for example, you ended up with like 1, 2, this would be infinitely many solutions. Okay, so basically you could have any possibility if you've got more equations than variables. Yeah. Well, one thing to notice, if you've got only 2 columns in your matrix, there is no z in some sense, because there's a column for x, there's a column for y, and there's a column for like the other side of the equality, but there is no z here. So the number of columns is the number of variables, the number of rows is the number of equations. Let's do like a word problem. So let's say a baseball game. Had 88 attendees, like fans. The price of a ticket is $4 for children, $5 for seniors, and $7 for adults. The total revenue, so the total amount of money they made, is $499. And let's say we know that there were twice as many adults as there were seniors. Okay? So how many tickets of each type were sold? So I'm gonna, I'm gonna have some sort of variables to kind of represent something in this problem, right? So we want to know how many, like the unknowns here, we have 3 unknowns. One is how many child tickets were there, how many seniors tickets, and how many adults tickets. So I'm going to let X be the number of child tickets. Y be the number of seniors tickets. And Z is the adult tickets. And now from this description, we need to get some equations. And you should write down as many equations as you can from this information. Can anyone tell me one of the equations? Yeah. Oh, sorry. A little bit louder. There could be something like that, but yeah, I'm not seeing quite that. Does anyone have another thought? Yeah? Number of tickets, yeah. Number of each ticket, but the ticket prices are here. Yeah. Right, because the number of total attendees is 88, the number of all the 3 types. But there definitely is going to be something involving this $4.99. So the total amount of money they made was $4.99. So for every child ticket, they made $4, right? $4. $5 for every senior. $7 for every adult. So that's my second equation, right? And then I have a third equation from this. There are twice as many adults as seniors. What would I write for that? Yeah? Yeah, I don't know why I made adults Z, but I think it's actually Z is 2Y, or 2Y equals Z, but what? Yeah, I assume that's what you meant. There's twice as many adults as seniors, adults is Z, so yeah, Z is 2Y. So now I want to turn this into a matrix. Okay. And solve it with Gauss-Jordan elimination. So I take my first equation, which has coefficient 1, 1, 1, and I just write 1, 1, 1, and then 88. Right? My next equation becomes 4, 5, 7, 499. My third equation, I have to be a little bit careful, right? Because it's not really it doesn't look how I want it to look. So you kind of need to manipulate this a little bit. So you can rewrite this as negative 2y plus z equals 0. And now I can put it into my matrix. Okay. So note that you always want to have your equations written with all the variables on one side and all the numbers like 499 or 0 or 88 on the other side, right? So any questions how I came up with this matrix? Oh yeah, this would be totally the same. There's nothing wrong with this. Yeah. So it would just give you a 2 here and a -1 here. But you could, if you think about it, that's the same as just multiplying this row by -1, and that's allowed in our operations anyway. So that would be fine as well. You'll get the same answer. Okay. So now we row reduce. Or row reduce, in other words, Gauss-Jordan elimination. Okay, so the way I see this is I'm already pretty happy with this 1 here, right? I've got my leading 1 on the first row, and I just want to eliminate everything else in that column. So I'm going to take row 2 minus 4 times row 1. So now I get 1, 0. So this one doesn't change. Okay, but this will change because I'm taking 5 minus 4 ones, will give me 1. Taking 7 minus 4 ones will give me 3. Taking 499 minus 4 88s, which I need to look up, 147. So this 147 came from 499 minus 4 times 88. Okay. So now my first column is good. Second column, I'm actually already pretty happy as well. I've got a 1 sitting here. So what I'm going to do is I'm going to take row 1 minus row 2. Okay. The reason is that that's going to get rid of this 1 here. I'm going to also take, at the same time, I'm going to take row 3 plus 2 row 2. Right. So hopefully the process is becoming, I don't know, a bit clearer than it was last time at least. Right, I'm pivoting the second column, whatever that means. I'm trying to get a 1 in the second row, second column, and then eliminate, everything else from that column. So when you do this, the first column stays the same because I'm just, like, this is kind of the beauty of this method, that once I've got this first column to look like this, when I'm adding things or subtracting things from the other columns, it's just adding and subtracting zeros to the other rows. It's just adding and subtracting zeros. So I know this column's not going to change. Okay. This column, here I had a 1, and I'm subtracting this 1, so I get a 0. I've still got a 1 here. Here I had a -2, and I'm adding 2 1s, so I'm getting a 0. Right? That's still a 3. What am I getting here? Let's see how with me you guys are. So row 1, and I'm taking my original row 1, I'm subtracting row 2, I'm getting a -2, right? Taking that value minus the value on row 2, so -2. And here, yeah, 7. Right, because what I'm doing to row 3 is I'm adding twice what I have on row 2. So this was originally a 1. I'm adding 2 of those to get a 7. So that's 88. Oh, no, sorry, no, it's not. It's definitely not 88. Remember, I'm taking 88, I'm subtracting what I have here. So that's -59. This stays the same. Here, I have what I had before, which is 0. I add 2 of those, which is 294. Okay. Now my first 2 columns are pretty good. I want to fix up this last column. Any suggestions what I should do next? Yeah. I kind of see where you're going with that, but that's going to mess some stuff up. So you're subtracting 2 of these from here. The thing is, that's going to kind of screw up. I really like how this second column is already, and it's going to mess it up. Any other thoughts? Yeah? Yeah. So actually, that's how this kind of system works, is that you kind of, sort of once I've got these rows kind of sorted out, I actually don't want to add these things to the third row at all. I just want to take this third row and just get that to be a 1 by just dividing. So, or in other words, multiplying by 1 over 7. So 1 over 7 times row 3. You guys will get a lot of practice with this, so don't worry. Oh, sorry, this was a 3 still. So that should give 42 here. Okay, and now I've got this 1 here that I'm happy with, and now I just go to town and I eliminate everything in that column. So I'm going to take my next step, I'm going to do 2 steps at once, row 1 plus 2 row 3. I'm also going to do row 2 minus 3 row 3. Okay. This ends up as 25, 21, and 42. Okay, this was already 42, but so this 21 comes from 147 minus 3 times 42. And this comes from negative 59 plus 2 times 42. Okay, so now we win. So x is 25, y is 21, z is 42. Okay. Any questions about this? So if you got something, okay, you got to the end of this, but you're not feeling that confident about your answer, how could you check it? Yeah? That's a good start. So I would definitely do that. So if you add them up, if your answer is correct, they better add up to 88. Otherwise, your answer can't be correct. I would also just plug them into these ones as well, you know. If your answer is correct, they have to add up to 88. So check that this equation is satisfied. You could check this one, plug them in here. Do you get 499? Hopefully you do. Is it true that z is equal to 2y? Well, in this case, it's kind of easy to see that z's 42, y is 21, so it is 2 times y. And if you plug them into all your equations and they're all satisfied, then you can be pretty, I mean, in this case, you can be totally confident that it is correct. Right? Okay. Any questions about that? So to check, plug into the original equations. If unfortunately they don't satisfy the original equations, then you've got some painstaking work to see, okay, where did it go wrong? which is pretty annoying. Okay. Okay, any questions about that? Okay, so let's do another quick one that's going to kind of end up a bit differently than this one. Okay. So this time I'll just start with the equations, no word problem. Okay. So we've got two variables, right? And we've got three equations. So the first step is going to be just to write this as a matrix. So we got 2, 2, 2, 1, 3, -1. Or sorry, this should have been, sorry, I wrote this down wrong. This should have been a 3 here. So 2, 3, 2, 1, 3, -1, and 1, -1, 3. Okay. With these problems, there's not just one way to do it. So there's always multiple different solutions. Like here, what I could do is I could take my first row, I could divide it by 2. That might be a nice thing to do. The only reason I'm not going to do that is because I don't really want fractions, but you would still get the right answer. What I'm going to do instead is I'm just going to switch these rows. The reason I'm talking about dividing this by 2 or switching the rows is I want a 1 in the top left corner, right? So I'm going to say row 1, let's swap it with row 2. Got 1, 3, -1, 2, 3, 2, 1, -1, 3. So remember, this is one of our allowed operations. We can just switch the rows. Yeah. That probably, to be honest, would have been smarter, but you know, at the end of the day, there's sort of no wrong way to go here. There are just some ways that are maybe better than others. But as long as you apply the operations correctly, we're going to get there anyway. But yeah, that's a good point. It'll give you, if I subtracted this one, it'll give me a nice 0 there, which would be nice, but oh well. Okay, so now I'm going to take row 2, I'm going to subtract 2 row 1s. I'm going to take row 3, subtract row 1. Zero, -3. Be careful with negatives, right? 2 minus 2 times -1 is 4, right? Row 3, 0 minus 4, 4. Does this look right to everybody? Okay, just arithmetic. Okay, so I'm going to now divide this by negative. Well, there's different ways I can go about this, but if I really wanted to avoid fractions, I might want to switch these and then divide by -4, but well, let's be brave and deal with fractions. Okay. So now I'm going to take row 1 minus 3 row 2 And I'm going to take row 3 plus 4, row 2, just to take this 1 and use it to kill everything. So 1, 0, 3 maybe? Yeah, I think so. If I'm making some arithmetic errors here, let me know. I don't really want to do this, but okay, what's 4 over 3 is 12, sorry, 4 is 12 over 3. I'm now going to, from that, subtract 16 over 3. I'm pretty sure that's negative 4 over 3, but correct me if I'm wrong. Whatever it is, it's not 0. I'll tell you that. Well, and that's relevant here, because if I've got 0, 0 here, and this one's not a 0, no solution, right? So, right? Because this is saying 0 equals negative 4 over 3. That can't happen, right?